Hello everyone, this is the fifth lecture of our course EEE 4851 Advanced Communication Techniques. So in this lecture we are going to talk about code division for multiple access or CDMA. And these are the books I followed for preparing this lecture. So you can go through them if you want. Let us start. So previously in the first lecture I think I discussed somewhat briefly about code division for multiple access. So we know at least a little bit what is code division for multiple access. So here we are going to discuss about that in detail. And this particular technique, this was very popular in mobile communication systems starting from 2G then 3G. So this CDMA was invented in 2G mobile communication systems in 1995. So we had a particular standard called IS-95. There we used code division for multiple access. So there we started using this particular technique, CDMA. Then in 3G communication systems, we heavily used these particular techniques. Right now, in 4G and 5G, the mostly used techniques is OFDM and MIMO. So CDMA is not that much used right now. Still, it is a very important topic to understand how the mobile communication systems have evolved so far. Okay. So before we understand what is CDMA, let us try to understand what is multiple access, because CDMA is a multiple access technique, right? So we know that in our wireless channel, the resources are limited, the amount of frequency we have and everything is limited. But in this limited channel, we want to accommodate various users, different number of users. So how can we do that? To do that, obviously, all the users have to share all the resources available for that channel. This phenomena of sharing of wireless resources, this is called multiple access technology. So from very early on, when we started our mobile communication systems, that journey, from there we had different multiple access techniques, like we had FDMA, frequency division for multiple access, then we had TDMA, time division for multiple access. So what are those? Basically, we are going to share the resources among the users based on different criteria. Like for FDMA, we want to divide the frequencies available in our channel and divide those among the users. That is called FDMA. Very simple, right? Then in TDMA, what we do, we want to share the time we have available for our system, right? So we have small time slot available for each user, so that the communication between different users are not causing any kind of interference to other users, right? So this is the basic idea of FDMA and TDMA. Particularly FDMA was established in first generation of mobile communication systems. Then in 2G we started with TDMA. So we had a system where we were using TDMA and FDMA together. Then also in 1995 we had CDMA coming to our second generation of mobile communication systems. So now the question is how this code division for multiple access or CDMA is different from FDMA and TDMA. CDMA itself is also a multiple access technique, as you will see. So how CDMA is different from FDMA and TDMA? To understand that, you see here in this figure we have in FDMA, the division is happening or sharing of the resources happening in frequency domain. For TDMA, this thing is happening in time domain. But for CDMA, you see all the users can get access to all the frequency and time available for our system or channel. Now what happens is, CDMA uses spread spectrum techniques like we discussed in our previous lectures. So in spread spectrum techniques, we know there should be spreading codes. Now for all the users residing in the same channel using CDMA, all the users will have a specific unique spreading code assigned for them, right? And because of that special unique spreading codes, there will be very minimum to even zero interference among the users. That is the basic idea in code division for multiple access. So Basically what happens in CDMA, obviously multiple users will use a common channel and they will use spread spectrum technique. And we know when we use spread spectrum technique, our transmitted signal will get a larger bandwidth, right? As always. And all of the users, you know, as we have multiple users, each of them will have a unique spreading code, and that will spread their signal obviously. But as the spreading code has a very special criteria, that is all of those codes will be orthogonal to each other. As a result, what will happen? The transmitted signals will not interfere with each other in CDMA. Even though multiple users are communicating at the same time in the same channel, because all the codes they are using are orthogonal to each other, there will be very minimum to even zero interference among the users. So this is just a brief understanding of how code division for multiple access works, but now we are going to understand in detail how code division for multiple access works. So let us start with that. So first of all, we will understand the working principle of CDMA in detail, basically. So to understand that, here we have an example where we have three users, A, B, and C, who are accessing the same channel. Okay, so we have three users in a channel, and as we know, CDMA means there will be spreading codes assigned for each user. So each of these users will have a unique spreading codes. These are shown here. Okay, so this is the spreading code for user A, this is for B, this is for C, and you see, if you look at this 1 2 3 4 5 6, all of these spreading sequences have a length of 6 chips, right? So now these are the codes assigned for three users. Now how to actually transmit any kind of information using these spreading sequences? So just from the understanding of previous lectures, we know whenever we want to transmit binary 1, we just simply transmit the spreading code when we are communicating using spread spectrum, right? And when we want to transmit binary 0, what we do? We just take the complement of our spreading sequence, then send that. To understand that, look at this example. Like for user A, this is our spreading sequence, right? If I want to transmit, that means if user A wants to transmit binary 1, then what he has to do? He has to transmit the same spreading sequence that is assigned for him. Exactly that one will be transmitted, right? Like here. But if he wants to transmit binary 0, what has to be done is he has to take the complement of his spreading sequence, then transmit that. So you see, this one is actually complement of his spreading sequence, the spreading sequence of user A. So in this way, user B and user C can do the same thing whenever he wants to transmit binary 1 or binary 0. Okay, so that is the basic step. So now using this process, user A or B or C can transmit any kind of information. Now that is transmission, but how to actually receive that? Using the same concept of spread spectrum, we are going to receive each of these signals or each of this information transmitted from either A or B or C. So let us try to actually explore that, how that happens. So let us consider a case where user A is trying to transmit any kind of information which is R of A. Okay, so it is called encoded message because we are using spread spectrum technique. There will be a spreading sequence, using that our information will be encoded. So that encoded information is R of A, and at the receiver side, intended receiver wants to receive this signal, somehow decode this signal. To do that, what he needs is the spreading code of user A, which is C of A. If the intended receiver has that code, what he can do? He can just take R of A, the transmitted signal, or you can also say received signal, from the point of view of the receiver. So that received signal R of A, if correlated with C of A, should actually extract the information transmitted from user A. That is the basic idea, right? We want to correlate C of A with the received signal R of A. So let us look at that process, how that happens. So let us assume first user A is trying to transmit binary 1. So what should happen? Whatever spreading sequence is assigned for user A, he should just transmit that particular spreading sequence if he wants to transmit binary 1, right? Like we described in the previous slide, that whenever user A wants to transmit binary 1, he has to transmit the exact sequence assigned as the spreading sequence, and for transmitting binary 0, we are going to transmit the complement of our spreading sequence. So that is what is happening. Here you see user A wants to transmit binary 1, so this is user A's spreading sequence. He just transmitted this one. This will be received by the intended receiver, and at the receiver we are assuming that the receiver has access to that spreading code of A, which is C of A. So that is written here, and we know this C of A should be correlated with R of A to extract the information transmitted from our user A. So what is correlation? Basically we have to first multiply R of A with C of A, then sum up for the whole duration of the period, right? Period of the whole spreading sequence, right? So this is the transmitted signal, this is the spreading sequence of user A. First of all, let us multiply. So 1 1 multiplied, so result 1, minus 1 multiplied with minus 1 1. So in this way all the values are taken, then this whole sequence should be added together to take the total summation. So that is done here. So this is the correlation of C of A with R of A, which is called S of A. So correlation at the receiver, S of A is equal to 6 whenever user A transmit binary 1. Now what if user A transmit binary 0? Then we know what he has to do is user A has to take his spreading sequence, then he has to take the complement of that, then transmit that, right? So you see this was the spreading sequence, complement of that should be obviously this one. So you see 1 complement minus 1 complement 1. So this is actually denoting data bit 0 for user A. So user A transmitted this signal, and to decode that again at the receiver, what we will do, we are going to use the exact spreading sequence of user A, C of A, to decode that signal. So we are taking this one, then correlation of C of A with R of A should be done. That is done here. So minus 1 multiplied with 1 is equal to minus 1, 1 multiplied with minus 1 is equal to minus 1. So in this way all the values are multiplied, then taking the whole summation here, we are getting minus 6. So all the values are minus 1 here at the result, all the values are 1 here. So for both of these cases we got different value of correlation. For one case, whenever user A transmits binary 1, we are getting 6, and when user A transmit binary 0, we are getting minus 6, right? So let us remember that for now. Now here one thing to actually understand is, you see we are saying correlation is S of A, right? So this subscript A in S of A basically indicates that we are correlating the received signal with user A's spreading code. So whatever signal we receive, we don't know about that, but we are correlating that signal with user A's spreading code. So whatever spreading code we are using in our correlation, that should be here as subscript. So if, let's say for example, if we try to correlate with the code of user B, which is C of B, then this notation should be S of B, right? So in this way we have to denote our notations. Now let us try to actually understand what is happening in the previous slide. So you see our correlation value, this value is we got plus 6 and minus 6, but if you look at the previous slide, the maximum value possible for this correlation is 6 and the minimum value is minus 6. Because all of the values are 1, we cannot get a much higher value than that. Same goes for this one, this is the minimum value. So we can say whatever values we take for correlation, this correlation value will always reside between +6 and -6. That is the maximum and minimum value for this particular correlation, right? So whatever value we get as our received signal, the correlation will result in a value that is within +6 and -6, right? And that is the maximum and minimum value, obviously +6 and -6, which is received whenever we received signal A spreading code or the complement of that. Try to understand that. So previously you see here for transmitting binary 1, what we did, we actually received the spreading sequence of user A, and when 0 was transmitted, we got the complement of user A spreading code, right? So the spreading code was resulting the maximum value +6, and the complement of that after correlation was resulting the minimum value. So maximum and minimum value for this particular correlation happens whenever we get signal A spreading code or the complement of that as received signal. Okay, so using that interpretation, what we can interpret is basically this: if the correlation S of A produces a value of +6, then we can obviously say the received signal is binary 1 transmitted from user A, right? Obviously. And whenever we receive -6, we can say the received signal was, or received message was, binary 0 transmitted from user A. And if anything other than that happens, we can say whatever information we are getting, that is just an error. Okay, let's say like +1 or +2 or maybe 0. These values are basically garbage. We are not actually getting anything from that. So we are intending the maximum and minimum value for interpreting that result as binary 1 or binary 0. That is the ideal case basically. We will see what happens when we don't have ideal cases like this one. But we understand what is happening here, right? Now, why should we go through all this complicated process? So the reason becomes clear if we see what happens whenever user B is sending some kind of information and we try to receive that using the spreading code of user A. Okay, so how that happens, let us see. So here we are observing a different scenario where user B is transmitting some signal R of B, and to decode that at the receiver, what we are doing, we are using user A's spreading code, which is C of A. So can we actually retrieve that signal? Let us try to understand that. So here same thing is happening. Whenever user B wants to transmit binary 1, this is the signal he has to transmit, because this is the exact spreading sequence assigned for user B. So we want to transmit data bit 1, that's why we are sending this one. And this particular 6-bit sequence is spreading code of user A. Okay, so that one. So we have to correlate C of A with R of B. To do that, what we do, we just multiply, then sum. So after multiplication, this is the sequence we get. After summing it up, we get the result as 0. As you can see, there are 3 plus 1s, 1, 2, 3, and 3 minus 1. As a result, the result of the correlation is 0 for whenever B transmit binary 1. And when user B transmit a value of binary 0, then we have to take the complement of spreading code of user B, which is done here. You see, this is just the complement of this particular sequence. And to decode that, again we are doing the same thing. We are taking the spreading code of user A, which is this one. After correlation, again we will see we are getting the resultant value as 0 for the correlation. So you see, S of A value is for both of the cases is resulting in a value of 0. So we can say the signal, the unwanted signal from user B is not showing up at all. So why we are calling this unwanted signal? Okay, because let us say if in a scenario both of these user A and B are both using the same channel at the same time, so they will transmit 2 signals simultaneously at the same time, right? So what will happen if I want to retrieve one of the signals from that? Will the other signal cause some kind of interference? To understand that, you see, consider this scenario where user A is transmitting a value of binary 1 and user B is transmitting a value of binary 0 at the same time. Simultaneously, they are transmitting these two signals at the same channel. And say at the receiver, our intended receiver is trying to retrieve user A's message using its spreading code. So we have access to our user A's spreading code. Using that, can we actually decode the signal? Because we have two signals interfering with each other in this situation. Now to understand that, look at this particular table. So obviously transmission from A is data bit 1 because it is transmitting binary 1. So that is just this particular sequence, the spreading sequence of user A. For user B, data bit 0 should be transmitted. So here we are taking the complement of spreading sequence of user B, and at the channel both of the signal will get mixed up, right? So we have to add all of them up. So we are just adding here, you see, combined signal R of A, B. So we are calling combined signal where A and B, both of the signals are together, that is R of AB. So this is what happening at the channel, which is, you see, so if I just add them, here we are getting 0, -1, -1, so -2. So in this way, all of these are added up, and this is the combined or composite signal we are getting at the channel that will be received by our receiver. And what will the receiver do? Receiver will have the spreading sequence of user A. It will try to correlate the received signal, this one, with the spreading sequence of A. So that is done here. If you just take the correlation, so you see multiplication then summation. So multiplication 0, -2 multiplied with -1, 2. So in this way, all of these are multiplied, then the summation is taken. We have 3 2's, so the summation is resulting in a value of 6. So the correlation results in a value of 6. Now here, you see, this correlation results in a value of +6, which can be interpreted as binary 1. Obviously, just like before, we can again here say binary 1 was transmitted from user A, which is true, right? We have recovered user A's message without any interference from B signal, because we know user A transmitted a data bit of binary 1, and which is received here. +6 means we have to interpret that as binary 1 transmitted from user A, right? So this is how here you see we have no interference caused by user B, even though they are both together residing in the same channel being transmitted, right? So how this is possible? This is possible because we have two codes which are orthogonal to each other. So here the code of user A, C of A and C of B, they are actually orthogonal to each other. That means if I take the correlation for these two different codes, the resultant should be 0, which can be practically shown here. So this is the spreading code of user A, this is for user B. After taking the correlation, that value is resulting in a value of 0. So for this kind of codes, if we have different signals available at the channel, even though multiple signals are together residing in the same channel, still if we have the specific code for a specific user, we can retrieve that signal without any interference from other users. That is the idea of orthogonal codes. But you see, when we have multiple users, we should have multiple codes available where all of them are orthogonal to each other. That is not that easy to get. As a result, in practical scenarios, what we have codes that are not exactly orthogonal to each other, but they have some kind of property where correlation will result in a value which is very less. Okay, so previously here we saw that for orthogonal codes, the correlation results in a value of 0, which is the ideal case. But as we don't have a lot of codes like that, we in practical scenarios what we do, we take some codes which are not exactly orthogonal to each other, but after taking the correlation between them, that will result in a very small value, which is also desired, right? That will minimize the interference between different codes, different signals. So such is the case for the code of user B and user C, as they are not exactly orthogonal to each other. If I take the correlation between these two codes, you will see the resultant value is +2, which is not exactly 0. So this kind of codes can also be used, but they will cause some kind of interference in the channel, and obviously we have some techniques to mitigate those if the amount of interference is much less. So for this kind of scenario, what can happen? You see, to understand that, let us assume that user B and user C are transmitting at the same time at the same channel. So for that case, user B is transmitting binary 1, user C is transmitting a binary 0 in the same channel simultaneously. And at the receiver, some receiver is trying to retrieve user B's message using its spreading code. Then what will happen? For that case, you see, transmission from B is a data bit of 1, which is this one. Again, to transmit binary 1, we transmit the exact spreading sequence of that user, and to transmit binary 0, we transmit the complement of that, right? So for transmission from C, data bit of 0, so we are just taking the complement of the spreading code of user C. You can check that if you want. So at the channel, these two signals will get mixed up. So the combined signal R of BC is this one. We just adding all those up, and this is the composite or combined signal at the channel. This will be received by our receiver, and our receiver is trying to retrieve the information transmitted from user B using its code C of B. So user B's spreading code is this one, and after taking the correlation of C of B with R of B of C, we are getting the correlation which is this one, right? Which will result in a value of +4. So S of B, which is the correlation at the receiver, is resulting in a value of +4. So what is that saying to us? As we want to retrieve the signal transmitted from user B, we want to interpret the value of binary 1. So we should expect a value of +6 ideally, just like our previous explanation. But here we are getting +4. We are not getting +6. This is because, you see, because of the message of user C, there is a small error of magnitude 2 in our system. Because of that, we are not getting exactly +6, we are getting +4. Even after that, we can actually interpret this result as transmission from user B, because in reality what will happen, CDMA receiver actually can filter out this small amount of error or interference coming from different users, because we have this kind of techniques, and obviously the magnitude will be much less in real scenario compared to the actual signal. So this is the basic working principle of code division for multiple access. We have different unique codes assigned for each users, which are orthogonal or almost orthogonal to each other. As a result, there is much less interference, or sometimes even zero interference among the users, so that we can retrieve the signals as we want. Okay. So now that we understand the basic working principle of CDMA, we can now see the overall picture, I mean the overall workflow of CDMA system. Now here, this kind of CDMA system is graphically represented here, and this is just a simple BPSK based CDMA system where we have n users in the same channel transmitting using different orthogonal codes assigned for each of them. So these orthogonal codes are here actually, C1, C2 up to C of n for each of these users. So user 1 is trying to transmit x1, user 2 is trying to transmit x2 up to x of n, you see. So, and for each of the users there will be a unique specific orthogonal or almost orthogonal codes assigned for them, which is C1, C2 up to C of n. And using these codes, first of all, we have to spread our signals. So all of them will get spread, and that signal will then get multiplied with cos 2 pi fct for digital modulation, right? So all of them will get modulated with the same signal cos 2 pi fct, and that will be transmitted. So we have different signals available here, y1, y2 up to y of n, and also at the channel there will be some noise. All of these things will get combined at the channel, right? So that combined signal is actually this one, which is y of t, y1, y2 up to y of n, and also noise. All of them will be here, and this will be received by our receiver, right, which is y of t. And at the receiver, if we have the spreading sequence of our intended user, whichever signal we want to retrieve, we can just easily extract that, right? So here, for an example, we are showing that we want to retrieve the signal coming from user 1. So we have to use that particular spreading sequence, C1 of user 1, right? So that is done here. First of all, obviously we have to again demodulate our signal using cos 2 pi fct again. So after doing that, whatever signal we get here, that has to be disparate using C1 of t. And after doing that, we will see that we are getting the desired signal x1 of t transmitted from user 1. This is happening because as all of the codes we are using in this channel, C1, C2 up to C of n, these are all orthogonal to each other. As a result, after this spreading process, there will be no interference coming from other users. As a result, we are retrieving the signal of x1 of t. So this is the overall workflow of CDMA. Now let us try to solve a mathematical problem related to CDMA. So this particular example is taken from your Starling's textbook, problem number 7. So let us try to read the question first, then we will understand from this graphical representation. So the given figure depicts a simplified scheme for CDMA encoding and decoding. There are 7 users, all using CDMA with a spreading code of 7 bits. So as you can see, there are 7 users, user 0, 1, 2 up to 6. All of them are trying to transmit 1 bit of data, like binary 1 or binary 0. For that, they have been assigned some spreading sequences of 7 bits duration, right? If all 7 users transmit a data bit in the form of a 7-bit sequence, the signals from all users combine at the receiver so that 2 positive or 2 negative values reinforce and a positive and a negative value cancel. This might sound a little bit complicated, but basically what they're trying to say, you see, all of these users are transmitting the signal in the same channel. As a result, all the signals will get mixed up, will get combined. So that combined waveform or composite signal is this one at the channel. So all we have to do, we have to actually add all of them up, and then we will get the combined signal at the receiver. And if this whole thing is looking very complicated, basically this is just bipolar representation. So for all of these cases, the middle one is 0, this one is +1, this one is -1. So this is the spreading sequence in bipolar representation. Same goes for this one also. We will show how this is happening, how this combined signal is coming out. But first, just let us try to read the question. So to decode a given user data, the receiver multiplies the incoming composite signal by the spreading code of that user, sums the result, and assigns binary 1 for a positive value and binary 0 for negative value. So we will understand what they are actually trying to say here, but let us try to understand what are the questions. So what are the spreading codes for the 7 users? So we have to find out the spreading codes for each of these users. Then we have to find the receiver output for user 1 and the bit value assigned. We have to do the same thing for user 2 also. Now, from this figure, try to understand what is happening. So here you see we have 7 users. All of them are trying to transmit 1 bit of data, either binary 1 or binary 0. And for that, this is their encoded signal. This is the exact 7-bit encoded signal. Basically bipolar representation. So we can say this particular portion is +1, this is -1, and this is 0. And after all of these signals are actually formed, they will be transmitted in the same channel. As a result, what will happen? At the channel, all of this signal will get combined, right? So as a result, what is happening? This is the combined or composite signal we are seeing, and here this is the reference or zero level, right? And if we add all of them up, that will result in a value like this. So you see, this can be shown actually. So you see, so this is 1, 2, 3, 4, 5. This is -1. So 5 minus 1 is equal to 4. Again +1. So 5. So total +5 should be for first time slot. So 1, 2, 3, 4, 5. So this is +5. So in this way, all of these are added together. So this is 1, this is 1, this is -3, this is 1, this is -3, this is -3. So this is the total composite signal coming from all of these signals added together. And now at the receiver, this composite signal will get received, and as a result, we want to retrieve one of the user signals, obviously, right? How to do that? Let us say, for example, we want to retrieve the signal coming from user 0. So for that, we use the user 0 code, which is this one. So here there should be one line like this. So this is 0, this is +1, and this is -1. So this is just bipolar representation, and we have to correlate the code of user 0 with this composite signal so that we can retrieve the signal of, or the information coming from user 0. So that is done here. So first of all, we have to multiply these two signals. You know, correlation means multiply then sum. So multiplication process is this one. So we are just multiplying these two waveform. So this waveform multiplied with a +1 should be here. This waveform multiplied with a +1 should be here. So in this way, this is done. You see, for this one, this is -3, but the waveform is negative -1. So this will be multiplied and the waveform is shifted upwards. So vertically it is shifted. So in this way, the whole waveform is done, and now we have to take the summation for this one. So what is the summation? So obviously this is 5, I think. This is 1, this is 1, this is 3, this is -1, this is -3, this is +3, right? So you have to add all of these values to get my 9, right? So 5, 1, 1, 7, 10, +3, 13, and -4. So 13 minus 4 is equal to 9. Or you can do another thing, which is you can just count the number of boxes in the positive region and at the negative region. So how many boxes at the positive region? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. 13, and at the negative region 1, 2, 3, 4. So 13 minus 4, which is 9. So 9 is the result we got from this correlation when we correlate with user 0's code. And if you look at the previous statement, we said that after correlation, we basically assign binary 1 for positive value and binary 0 for negative value, right? So we have got +9, which is a positive value. So we will interpret this result as user 0 transmitted a value of binary 1, which is true, right? User 0 transmitted binary 1 from the transmitter, right? So this is just worked out for us for user 0 as an example. We have to do the same thing for user 1, user 2 for this example problem. So let us try to do that. So the first question is, what are the spreading codes for the 7 users, right? Because spreading codes are not actually given here. We are just looking at the encoded waveform we want to transmit for this data values. Okay, so let's say, for example, for this data value of 0, we are trying to transmit this waveform, but the spreading sequence is not exactly this waveform for user 1, because we already know from our previous understanding in the previous slides, when a user wants to transmit data value of binary 1, he simply transmit his spreading code. However, when the user wants to transmit binary 0, he has to transmit the complement of his spreading code, right? So for the cases whenever we are transmitting data value 1, obviously whatever waveform we are seeing here, this is the exact spreading code for that user. So for user 0, this is the spreading sequence, right? Exactly like the individual user waveform. But for the next one, you see data value 0 was sent. So obviously whatever the spreading sequence was assigned for user 1, he has to take the complement of that, and that will be transmitted as this waveform, right? So we have to take the complement of this one to get the spreading sequence of user 1. So that is done here. So you see this one is exactly complement of this one. So in this way, all the user codes can be retrieved because we know the data value and also the waveform transmitted. Using those, whenever we have data value of 0, we can just take the complement of this one, and whenever we have 1, we can just take the whatever waveform we have, that is the exact spreading sequence, right? So this is very simple. So we can also represent that in written form. What are the specific spreading sequences for each of the users? Okay, so as this is just a bipolar representation, 1 1 1 1 1 1 minus 1 minus 1 minus 1 minus 1 1 minus 1. So in this way we can just represent that in written form also. Now for the next one, basically we have to find the receiver output for user 1 and the bit value assigned. So previously whatever example we have seen for user 0, that has to be done for user 1. So we have to take the spreading code of user 1, the composite signal whatever we have got previously, that will be identical here also, because the same signals are being transmitted from the 7 users that will get combined here. And to retrieve the signal from user 1, we have to take the user code of user 1, right? Then we have to do the correlation, simple correlation, that will result in a waveform like this. Again here I am repeating that basically this is just the reference value is here 0, and these are just positive values and these are just negative values, and all of these small squares are representing value of 1 vertically and also 1 horizontally. So obviously from that you can just take these two waveform and multiply these two to get this waveform, and then finally we have to calculate, and that means sum up the waveform. We can again do that. So we have 1 2 3 4 5 plus 5 boxes at the positive region, and 1 2 3 4 5 6 7 8 9 10 11 12. So minus 12 at the negative region. So 5 minus 12, which is, so we are getting minus 7 from this correlation, right? So as this value is a negative value, we can interpret this result as binary 0. So we can just interpret that user 1 transmitted a value of binary 0, which is true because user 1 transmitted binary 0 here. So our result is correct. Then we have to do the same thing for user 2. Whatever we have done for user 1, we have to do the same thing. So everything is identical here also. We just have to take user 2's code, I mean the spreading code, then correlate with our composite signal to get the result of user 2. So for that, you see, after multiplying, we are getting the composite signal like this one. Then finally we have to just take the summation from this waveform, I mean just area under the curve, which should be something like this: 1 2 3 4 5 6 7 8 9 10 11 12. So plus 12, and at the bottom we have 1 2 3 4, so minus 4. So 12 minus 4 is equal to 8, which is our correlation result for user 2. And as this is a positive value, we have to interpret this result as user 2 transmitted binary 1, and which is true. Binary 1 was transmitted from user 2. In this way we have to calculate for this mathematical problem. Okay, now let us discuss about the orthogonal codes which are used in CDMA, how they are generated, how they are used, these kind of things. Now let us take two codes, C1 of n and C2 of n, which are said to be orthogonal. This will be true if this particular expression here, this results in a value of 0. that is taking the product of C1 of n and C2 of n and then summing that over the duration of their period. If that results in a value of 0, then we can say these two codes are orthogonal to each other, where here n is the length or the period of each of the codes. So in simpler terms, we can say two codes are considered to be orthogonal if when their product is summed over a duration of their period, the result should be 0. For example, let us take two codes which are C of A and C of B, and we are saying they are orthogonal to each other. So these are the two codes, and then if I take the correlation, or in other words inner product, that value should result in a value of 0. So you see these two codes first multiplied in this way, then that multiplied result is added over their duration of the period, right? That is resulting in a value of 0. As a result, we can say C of A and C of B, they are orthogonal to each other. Now, how actually these kind of orthogonal codes are generated for CDMA? One of the examples of such orthogonal codes is Walsh codes. This is the most common types of orthogonal code used in CDMA applications. So how they are built? They are actually built from a family of matrices called Hadamard matrices. These kind of matrices are actually built recursively. So each member of the family is built from the previous member of that particular family. Okay, so it will start from this particular matrix H1, which is the first member of Hadamard family. So this is this one, just a matrix with a value of 0. Then after that, the next member of that family, H2, that will be formed by repeating this 0 horizontally and vertically in the new matrix, and we will diagonally we are going to put the complement of 0, which is 1, right? If this sounds complicated, basically this 0 will come here, right, as the first element, then horizontally and vertically this 0 value is copied, okay, and diagonally we are going to take the complement of this value. Okay, so this value will be replicated sometimes exactly similarly, sometimes taken as a complement. So in this way we are getting the second member of that family, H2. Okay, in this way recursively it will build upon itself and create new members for that family. So if I want to generalize this formula, basically the next member, which is Hn plus 1, will be built from H of n, the previous member of the Hadamard family, and basically we are going to just copy H of n horizontally and vertically, and diagonally we are going to take the complement of this H of n matrix. Okay, so here this portion is basically complement of H of n. So in this way we have to proceed and create new matrices. So using this generalized formula, we can actually generate new matrices from this family. Basically, you see the next member is this one, H3. So that is done from the previous member, which is this one, right? Previous member, previous matrix was this one. So we are exactly copying this one here and here, vertically and horizontally. And diagonally, we are just taking the complement of this particular matrix, right? 0, 0, 0. So you see 1, 1, 1, and 0. So in this way, we are creating the new matrix. So that is what written here. 3 of the 4 quadrants are replicated from previous smaller matrix, right? 3 of the 4 quadrants are replicated like this, but fourth one, I mean the lower right quadrant, the shaded one, this one is actually complement of this previous matrix, right? If you look at the previous one, you see previous matrix H2 was this one. So we are just replicating this one here, here, and here. So 3 of the 4 quadrants are filled up like this, but the fourth one is taken as the complement of the previous matrix. So that is the basic idea, very simple. Now, how we are getting the orthogonal codes from this one? We know we need to find out the Walsh codes, right? And basically each row of this Hadamard matrix represent a unique Walsh code. So you see for this one, the fourth member of Hadamard family, from this matrix, each of the rows are basically representing a Walsh code. So we have 1, 2, 3, 4, 5, 6, 7, 8. 8 Walsh code generated from this particular matrix, and each of these code has the length of 1, 2, 3, 4, 5, 6, 7, 8. So 8-bit long codes, and such 8 codes we have from this particular matrix. These are all Walsh codes. So now, what is the specialty of these Walsh codes we are generating from this matrix? Basically, each of the rows are representing one Walsh codes, and each of these Walsh codes are basically orthogonal to all other codes we are seeing here. All of them are orthogonal to each other. And also, if you take logical NOT or complement of one Walsh code and then try to compute orthogonality, you will see that is also orthogonal to other rows as well. So that is what we are getting from this particular type of matrix. And as I already told you, the length is basically can be calculated by the number of bits in each row, right? For each of the Walsh codes, 1, 2, 3, 4, 5, 6, 7, 8. So here for this matrix, all of the Walsh codes have the length of 8 bits. Okay. So now, even though these codes are actually represented as 0 and 1s, still whenever we want to calculate the correlation and want to use in our CDMA, we have to use bipolar representation, that is representing binary 1 with +1 and binary 0 with -1. That has to be done always if I want to calculate correlation. Now, what are the problems of this kind of orthogonal codes? I mean, always this kind of orthogonal codes should be used in CDMA, but still, practically not always this kind of codes are used. What is the reason behind that? This is because, there are two types of CDMA networks. One is synchronous CDMA network, another one is asynchronous CDMA network. Synchronization basically means the process of aligning the timing of the receiver with the timing of the transmitter. Because you see, whenever we transmit a signal, that won't be instantaneously received by our receiver. There will be some delays, right? So a receiver has to determine the beginning of the transmitted signal so that he can actually use his spreading code to decode that signal. So there should be some kind of synchronization in time domain. Now in CDMA, there are some networks such that already inherently there is some synchronization method so that the transmitter and receiver is properly synchronized using some kind of electronic circuit. Okay, these are synchronous CDMA network. And some other circuit, there is no prior synchronization available. We have to do that ourselves using the property of our orthogonal codes or pseudo noise codes, this kind of thing. So that is the difference between synchronous CDMA networks and asynchronous CDMA networks. Now, for our Walsh codes, the orthogonal codes we are generating here, the autocorrelation property is very poor. If you remember, we discussed about autocorrelation property of random signals in the previous lecture. So basically, autocorrelation means correlation between different shifts of a code, right? And we saw that for random signals, we have a very desired autocorrelation property. Basically, the desired autocorrelation property was something like this, if you remember. So we had some figure like this, where we represented the autocorrelation R of tau with respect to the delay parameter tau, right? So this is the delay parameter. And we said whenever we had this in this region, tau is equal to 0, that is no shift, at that point we had a very high correlation. But after that, if I just change the value of tau, that is correlation between different shift of a particular code, then this value was very low, which is almost equal to 0, right? Then after reaching one period, again we are getting the spike, right? That was the desired property, autocorrelation property of PN sequence, right? But this is not a PN sequence. Walsh codes are not PN sequence. As a result, we are not going to get this kind of desired behavior from Walsh codes. Therefore, if prior synchronization is not provided, like in asynchronous CDMA, Walsh code cannot achieve synchronization. So what happens when we use PN sequences for spread spectrum? This kind of synchronization can be achieved by correlating the receive signal with a locally generated PN sequence that is shifted in time. Because for PN sequences, the autocorrelation property is such that R of tau is maximum when tau is equal to 0, and for other values, for tau not is equal to 0, we have R of tau is equal to almost equal to 0. If you remember from our third property of randomness, we said that for PN sequences, whenever the value of tau, that is shift in time, is 0, that is identical to signals like this, let's say, we are just correlating with each other. That will result in the maximum value, as we said here. And if I shift one of them, so something like this, maybe like this, you see, identical signal but one shifted in time. Then if you take the correlation, that will be something like this, R of tau, but there will be some finite value of tau. That should result in a value of 0 for PN sequences, for any random signals, ideally. So as a result, what happens? We can actually detect the correct alignment of signals, or synchronization can be achieved, because the point of maximum correlation indicates the correct time alignment, allowing the receiver to correctly demodulate the received signal. So we have to just wait for the correct alignment. Whenever we get the maximum peak for correlation between the received signal and our locally generated PN sequence, then we can say we are correctly aligned. Our synchronization is done. So in this way, PN sequences can minimize this problem, but Walsh code cannot do that. That's why orthogonal codes are not always desired. We practically, most of the time, we actually use different special PN sequence that will fulfill some of the properties of our Walsh codes, as well as PN sequences as well. Okay, so that is what is written here. Orthogonal codes like Walsh codes are only suitable for synchronous CDMA network, as I just said. But whenever we are dealing with asynchronous CDMA networks, we have to use special codes which have some property of PN sequences as well as some kind of orthogonality. So these kind of codes are actually called gold sequences, which we will generate afterwards and see how that works. Okay, now gold sequences. So in the previous lecture, we discussed about different type of PN sequences like maximal length sequences, then also non-maximal length sequence. And there at the end, we discussed that maximal length sequences are the most preferred codes to be used in spread spectrum. This is because they had the longest possible sequence length, and another reason was they exhibit a very low autocorrelation property, right? Now, in CDMA system, M sequences are not the optimal ones, because you see, for CDMA, we don't need just one code. We need multiple codes available for different users residing in the same channel. That is the problem, right? We have to generate multiple codes, and these multiple codes should have some specific properties. Like, we have to construct a family of spreading sequence, one for each users, where all the codes will exhibit a very low cross correlation with each other, because we are trying to mimic the property of orthogonal codes. And orthogonal codes, when taken correlation with each other, they result in a value of 0. So orthogonal codes has these kind of properties, and we want to use our PN sequences or M sequences in this case to behave like that orthogonal codes. As a result, they should also exhibit, if not 0, at least some low value of correlation. That is, very low cross correlation property of this kind of particular codes. Okay, so we are seeking that property for our codes, right? So how to get that? We already know that M sequences do not satisfy this criterion because M sequences have low autocorrelation property, but when it comes to cross correlation, we need multiple codes such that they will have very low correlation with respect to each other. This is not done in M sequences. We need a particular code, a popular set or subset of M sequences which are called gold sequences. Okay, so we have to generate that. To do that, basically we are going to see in details how they are generated, but the general idea is that these are generated by XORing two M sequences of the same length with each other. Okay, so here you can see an example of a gold sequence generator. So already you can understand this is built using two linear feedback shift registers. Each of them have length of 5 bits, right? So 5-bit shift register with some feedback. So these two particular circuits obviously are connected using this XOR gate, and finally we are going to get the output signal, right? Now for this particular circuit, initially we are going to take the initial condition as 1 1 1 1 1. So all ones factors for this LFSR and this LFSR as well. Okay, then we will start proceeding with our generation of gold sequence, right? Now basically, you know, whatever we generate from these two LFSR will be XORed here, and finally we are going to get the output for our gold sequence, right? There will be some clock pulse obviously for these two circuits which are not shown here. Now how they are actually done, let us see that. So we want to generate multiple gold sequences from this particular circuit which will be used in the same channel for different users, and all the codes should exhibit a very low correlation with each other. That is the basic outcome we want to get from this one, right? So now very easy to understand from the previous lectures that these two particular circuits here, right? These two particular circuits here, these are just LFSRs, and they are configured in such a way so that they will generate M sequences. If you remember, for a particular LFSR, if it generates M sequences, then we can say if the length of that LFSR is n, then the length of a generated sequence should be 2 to the power n minus 1. That is the basic rule for maximal length sequence. So for this case, as both of them have the length of 5 bits, okay, so we can say 5, the length of the generated M sequence should be 2 to the power 5 minus 1, which is 31. Okay, so each of these LFSRs should generate M sequence of length 31 bits. This one also and this one also, right? So let us call this one LFSR1 and this one LFSR2. Okay, so from LFSR1, this is the particular sequence generated. You can check it yourself. And for the next LFSR, this one, this is the generated sequence. Okay. And already these two can be considered as two gold sequences for our number of gold sequences we will generate. Okay, so these two are the first two members of that family. And now how to get the new members, new gold sequences from this particular circuit? To do that, this XOR gate comes to play. Okay, so we have to take these two M sequences we have generated, and then if I just XOR these two together, I'm going to get another 31-bit sequence, right? So 1 1 will be resulting in a value of 0, 1 1 0, 1 1 0. You see, in this way we are getting the third sequences here, which is this one, right? So we have already got 3 gold sequences from this one. Now let us proceed. Now how to get more sequences from this one? To do that, we have to shift the second M sequences. Okay, so if you look at the previous one, you see here, this one, if I just shift this sequence to the left by 1 bit, then we are going to get this sequence like this. Okay, so this sequence is just exactly the previous sequence, M sequence 2, but we have shifted this to the left by 1 bit. A cyclic shift, you can say. So after doing that, we are again going to take the XOR of these two sequences. First sequence is identical as before, but the next sequence here generated from this particular LFSR is shifted to the left by 1 bit. This one. Then after that, you have to XOR these two sequences together to get another 31-bit sequence, which is, after taking the XOR, we are going to get this one. So now we have 4 different gold sequences generated from this one. So if you can shift the second M sequence to the left 1 bit by 1 bit like this, then you are going to get new sequence here. And if you then take the XOR between these two particular sequences, then you are going to get a new gold sequences at the third row, right? So that is the basic idea. You can just shift it towards the left like this, 1 bit by 1 bit by 1 bit in this way, and finally you are going to XOR these two sequences together, and finally you are going to get a new gold sequence. So that is what is done here. You see, this is the first M sequence, this is the second M sequence. After taking no shift, just XORing this together, we are going to get this sequence, right? Then for this particular one, we are going to shift this M sequence by 1 bit, then XOR M sequence 1 and M sequence 2, we are going to get this one. Then for 2 shift, then for 3 shift, like this, we are going to get, for each of these shifts, we are going to get a new gold sequences. And that can be done up to 30 shifts, because 31 shifts basically will return the exact identical sequence we started with for M sequences 2. So we have to stop at 30 shift. So that is the basic idea how we can generate multiple gold sequences from this particular circuit. And you see, this is what is written here. This process continues through all possible shifts with each additional 1-bit shift followed by an XOR producing a new sequence in the set. Okay. So for the given configuration, it can be shown that for any shift in the initial condition starting from 0 up to 30, so 0 shift up to 30 shift, a new gold sequence can be generated. Total 31 gold sequences plus these 2, right? And 31-bit shift is basically the identical sequence we started from for M sequence 2. Okay, so in this way, how many gold sequences can be generated for this particular circuit with 2 5-bit LFSRs? We can generate total of 33 gold sequences, because 2 initial M sequences are there, this one, and from this 0 to 30 shifts, we have 31 more gold sequences. That is total of 33 gold sequences. These 33 gold sequences will have the property that all of them will have a very low cross correlation property with respect to each other. That is the one particular behavior we are seeking from these gold sequences. Okay, so there are different codes like gold sequences which have this good cross correlation property as well as autocorrelation property, which are very good for CDMA to be used. So sometimes whenever we have proper synchronization available in our system, a CDMA system, we can use orthogonal codes. But whenever we don't have this kind of facility, we rely upon different pseudo-random codes like gold sequences, and another one is Kasami codes. These are used so that we have good cross correlation property as well as autocorrelation property, so that we can achieve the synchronization ourselves. That's all for this lecture. Thank you.